Hi guys, we've got a couple of sections we're going to cover for chapter 4 today. We're going to go through B and C. So kind of another long video today. Lots to talk about, but I'm excited to get into the earth, literally. All right, so just a reminder, geology, I almost said geography. Geology is the study of the earth, specifically the rocks and the dirt and stuff that make up it. Also, we talked about this before, this idea of uniformitarianism, and that's the belief that the processes that form the earth are very gradual and natural. They take a long time, but they're somewhat regular. Okay. There used to be this counter idea known as catastrophism, and it was belief that catastrophic events shaped the earth. Sounds intriguing to me. Sounds like something like a great flood, or even, God saying, "Hey, let there be land and water." And sounds like kind of catastrophic to me. Anyway, so there's two views. What happens, and we're going to talk about this in the next slide. But before I get there, I want to talk about this picture here. The processes that form the earth, in order for it to fit into the scientific worldview, they have to have taken place over many, 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 many years. Okay. So if you look at this picture in the background, that's actually Cedar Breaks National Monument in Utah. It's not the Grand Canyon, but it's similar to the Grand Canyon. According to secular scientists, this would have formed over thousands and millions of years with very, very slow erosion. Okay. With the worldview of the Bible, we can kind of look at something like this and say, yeah, maybe this was formed by a great flood. And when the flood came through and shook up all the dirt and everything, and it started to settle, it made these layers of sedimentation, and it swept a whole bunch away to leave this canyon behind. That works for my worldview. In any case, this thing is gorgeous, right? All right, so moving on. This young earth versus old earth idea. The young earth is what creationists believe, okay? The old earth idea comes from, like I said, this idea that the processes are so gradual and so slow. So based on the observations of what we see today, it's true that the natural processes that are working around us are incredibly slow. So scientists have worked backwards to determine how long the earth must have been around to fit the processes they see. And so their deep time view is their belief that the earth is about 4.5 billion years old. Okay. Whereas creationists only believe that the earth is about 6,000 to 7,000 years old. We put those big events in there, like the flood, to have quickly reshaped the earth. And so what we see now with our observation is very gradual, but we keep that large event like the flood in our interpretation, whereas secular scientists don't do that. So they have to go back much further. They have a theory known as the theory of plate tectonics, and it's this idea that the continents are actually moving, okay, on those tectonic plates, the pieces of crust we talked about last section. And they move incredibly slowly. So it fits into that idea of this really, really old Earth, okay? They go so far as to talk about this supercontinent known as Pangaea, and it really kind of makes sense. If you look at the continents, a lot of them look like puzzle pieces, like they would have fit together. But if you put the flood into place, and we'll read about the flood in class, maybe God did create one huge landmass. But when the flood came, the Bible talks about the water coming out from the ground, coming from the deep. Maybe it was so violent and catastrophic that it actually broke apart those continents. And so instead of it happening super slowly over billions of years, it happened very quickly and reshaped the earth that God created for us. Okay. Now, post flood, those processes are very slow, and that's what we observe. Okay. All right, so this gets us into this operational versus historical science debate again. Operational geology is using observations. It's what we see, and those processes are very slow. We agree on that. Historical geology kind of has all of the geologists believing that the world is very regular, that principle of uniformity, that the processes are following a pattern and a speed and a rate, okay? Secular scientists extend that uniformity into the past where we can't make observations and ignore the possibility of these big catastrophes. But then they also want to put that into the future, saying, okay, what we see now is what we're always going to have, and it's always going to be regular. But we can't really predict that. We don't know if a meteor is going to come and hit the Earth and cause all kinds of damage. We don't know what kind of massive earthquakes are going to happen and reshape the planet. We don't know what kind of catastrophic events might come and quickly reshape the Earth. Okay. All right, switching gears a little bit, we're going to get back into the talk about the layers of the Earth. So this is section C now. If you want to follow along, there's some good pictures in the book. Keep in mind, the deepest we've ever drilled into the Earth is only 12 kilometers. It's only about 7.5 miles. Okay. Mount Everest is just under 9 kilometers high. So if you turned Mount Everest upside down, that wouldn't even go as deep as the deepest we've drilled. Okay. But 7.5 miles versus 4,000 mile radius. Okay, so if you were to drill all the way to the center, very center of the Earth, you'd have to drill 4,000 miles. So we haven't gotten very close. We've not gotten past the crust. Okay, scientists learn a lot about the inside of the Earth from what they can't observe because we can't drill that deep. From earthquakes and the seismic waves and how they travel, the speed they travel through the Earth. Okay, so a lot of their interpretation, a lot of their ideas come from that data. The Earth is divided into 3 main layers. We've got the crust, the mantle, and the core, and you can see this in this diagram. The core we will talk about is divided into the inner and the outer core, but in general, we usually talk about the crust. It's like the eggshell. We talk about the mantle. That's like the egg white of a hard-boiled egg, and then the core, which would be like the egg yolk. Okay, so the crust is the very outer layer, and it is broken up. It's broken up into those tectonic plates. Okay, it's anywhere from 3 to 56 miles thick, depending on where it is. The crust continues under the ocean. So even if you look at the Earth, you see land and you see water. There's still land under the water. That's known as oceanic crust. The continents are known as continental crust. Okay, so the continental crust is much thicker than the oceanic crust because you already have to go far below the water. The crust under the ocean is much thinner. Okay, the continents are about 6 times thicker than the crust that's under the oceans. Let me get this funny name, MOHO. It's a capital M because it's actually named after somebody. He's the scientist that determined where the boundary is between the crust and the mantle. And he determined this by observing those seismic waves. He noticed that they started behaving much differently at this specific point. And so he said, all right, we're in a different layer. The crust ends here, and then we go into the mantle. And so that boundary between those 2 layers is known as MOHO. Go figure. All right, the mantle is a little more complicated. It goes from the MOHO, so that boundary, down to about 1,800 miles. All right. To give you a little perspective, if I was to get into my car and drive to Birmingham, Alabama, that's about 1,800 miles away. Okay. But remember, the radius, the depth to the center of the Earth is about 4,000 miles. So we're still not all the way down. We've got some specific layers within the mantle. We've got this thing known as the lithosphere, which is actually a combination of the crust itself and the very upper part of the mantle. So it's not just the mantle itself. Then we get the upper part of the mantle, and it's solid rock, okay? But it's different than the crust. It's a different kind of rock, and it moves with those tectonic plates. Below that, we get the asthenosphere, and it's about 125 miles thick, and it's starting to get hot enough that it's getting kind of molten. It's not totally melted, but it's starting to get kind of gooey. Okay, and then the very lower part of the mantle is even deeper than where earthquakes occur. So there's not really any seismic activity down there. Okay, and then that takes us to the core. The core is divided into the outer core and the inner core, and it's incredibly hot in both of those, almost as hot as the center of a hot pocket coming out of a microwave. The outer core is about 1,400 miles thick, and it gets anywhere between 7,200 and 9,000 degrees Fahrenheit. It is very molten. It's melted material. Okay. Now this is where it gets a little interesting. So the inner core is about 1,500 miles across. So if you imagine this ball in the middle of the Earth, the diameter of that ball would be about 1,500 miles. Okay, the center of that would be the very center of the Earth, but it's solid, even though it's hotter than the outer core. So the materials that it's made of are still in a solid state, and the reason for that is because they're under such extreme pressure. Okay, so the temperature is anywhere between 9,000 and 11,000 degrees Fahrenheit. The metals that make up the core, scientists figure it's largely nickel, and I don't remember. I'll have to get that in class. Anyway, those materials would absolutely be molten at those temperatures if they weren't under such a great amount of pressure. But all the other layers are pushing down on it, and so it's keeping those as a solid. And that's possibly where our magnetic field comes from. The core might be moving itself in there and producing that magnetic field. Okay, not a lot is understood about that. Here we go. Yeah, probably 85% iron and about 5% nickel. So two metals that would definitely melt at that temperature if it wasn't for the pressure inside. Okay, that's all I got for you guys. See you later.